Mefani as a bow, and this is my Physics 2212 Lab 4. So for the introduction, the purpose of this lab was to use principles of energy conservation and current to predict the behavior of circuits containing resistors in series and parallel, and to use multimeters to measure the actual values of conventional current and potential difference in these circuits, to examine the behavior of ohmic resistors and capacitors. And some of the results that we found were that the node and loop rule hold true. The current in an RC circuit is time dependent. Some physics principles we saw throughout the lab were that the node rule, current flowing into a node must equal the current flowing out of the node. And this is a result of the charge conservation. The loop rule, the sum of all electric potential differences around a loop is zero. This is also a result of the charge conservation. And then Ohm's law, the current through a conductor between 2 points is directly proportional to the voltage across the points. Some assumptions we made were we assumed the resistance of the ammeter was negligible, and we also assumed that the resistance of the wire was negligible. So when we created our circuit and we um, reversed the connections to one of the ammeters, we officially initially the ammeter read 19.6 amps, and we reversed it. It read negative 19.6 amps. So this is the connections of the circuit that we built. So here we measured the potential difference between different points on the circuit. So for AB we got 3 volts. For BC we got negative 0.2 volts. For CD we got negative 0.8 volts. For DE we got 0 volts. For EF we got negative 1.9 volts. For FG we got 0 volts. For GH we got 0 volts. And then for HA we got 0 volts. And this adds up because throughout the whole circuit, the net potential difference was zero, added up to be zero, which holds up for our physics laws. You can see this represented the graph they told us to draw, where you can see the potential difference rises and falls back to zero. Or the number 12, it says from your potential difference measurements in part 5 and the current measurements in part 6, calculate the resistance of each of the following circuit's elements. For part A, we got negative 0.8. For B, we got negative 1.9. And for C, we got 0. And for D, we got 0. So for the RC circuit, we investigated the RC circuit to observe how the capacitor charges. And we measured the time it takes for the capacitor to discharge. And for those measurements, we got, so it took about 12 seconds for the 10 ohm bulb to discharge, while the 20 ohm bulb took about 30 seconds. Some possible sources of error, human stopwatch error. So there's might have been some inaccuracy in timing the discharges of the different ohm batteries. And the batteries may have not been in best condition as they were used before us. Or what if you were doing this lab in real life and used an actual ammeter instead of an ideal simulator ammeter? What's the difference between the real ammeter and how it would affect the circuits you hooked it up to? If you did this lab with the real components, access the virtual link above to see if you can determine how it would behave differently from the real ammeter you used. So, so it wouldn't be the same because the online simulator doesn't account for certain things. Um, and then for the um, what if you're doing this lab in real life and you use the real battery to charge a real capacitor with no resistor in the circuit? How quickly would your ideal model predict the capacitor to reach full charge? Would this prediction happen in real life? Explain if you are completing this lab with real components using the ammeter to measure how long it takes to charge the capacitor when connect directly to the battery. Discuss why you measured it differently this time. So because batteries have resistors in real life, it'd be almost impossible for it to charge like instantly. So yeah.